네, 안녕하세요. 벌써 이틀째네요. 그래서 오늘 두 번째 키노트 소개를 하러 올라왔습니다. 전 이준환이고요. 오늘 소개해드릴 키노트 스피커는 제임스 포가티라는 유니버시티 오브 워싱턴 대의 교수입니다. 제임스 포가티 교수는 카네기 멜론에서 HCI로 박사를 받았고요. 그리고 지금 현재 유니버시티 워싱턴의 컴퓨터 사이언스 스쿨의 교수로 재직하고 있습니다. 그리고 이제 워싱턴 대학에는 더 그룹이라고 인터디스플리너리한 그룹이 있어요. 그래서 컴퓨터 사이언스와 인포메이션 스쿨, HCD 이런 여러 디파트먼트가 같이 이제 연구를 진행하는 그런 곳인데 거기에 디렉터를 맡고 있습니다. 다양한 HCI 연구를 수행을 해왔고요. 특히 새로운 인터랙티브 시스템을 만들고 평가하기 위한 도구를 개발하는 데 큰 관심을 가지고 있습니다. 그래서 Ubiquitous 컴퓨팅 인텔리전스 시스템 이런 쪽에 굉장히 많은 컨트리뷰션을 보여주고 있습니다. 그래서 지금 현재 HCI 분야에 가장 주목받는 연구자 중 하나입니다. 그래서 시그카이에서 수차례 체어를 맡아왔고요. 그리고 다수의 베스트 페이퍼와 어너러블 멘션을 수상하기도 했습니다. NSF 캐리어 어워드를 수상하기도 했고요. 그래서 오늘 발표할 주제는 데이터와 머신러닝이 HCI에 어떻게 사용될 수 있을지 제임스 포가티 교수가 오랫동안 연구해왔던 내용을 소개할 예정입니다. 다들 박수로 맞이해 주시기 바랍니다.
Thank you, Junwon. It's a real pleasure and an honor to be here today. And I want to talk some about everyday interaction with machine learning. Before I get started on that, if you're in the back or otherwise have any trouble seeing the slides, I've made a PDF available here that you can download if you'd like. So that's at http://tiny.cc/jayfo. And I'll leave those up if anybody wants them afterwards too. Okay, so the starting point that I want to begin with today is just the really incredible set of technological changes that we're all living through, right? This is really fascinating to us as designers and really fascinating to us as people living in this world, I think. At the core of a lot of this is Moore's Law. Right, and so we can plot lots of different things on that exponential curve. Of course, transistors, but also computing power in the world, storage in the world, the amount of information in the world, the information about each and every one of us in the world, the number of devices that each and every one of us encounters on a daily basis, and so on. All of these are on this same curve, right? And one of the things that follows from that is the arrival of ubiquitous computing. And so Weiser foretold this when he described this progression from the mainframe era, the many-to-one, many people sharing a single computer, into the personal computer era, right, the one-to-one, each of us having our own computer, and into these later stages where the many computers to one person, and then what he finally called ubiquity, which was many people connected through many devices, right? And so the devices disappear and we become connected through them to each other. And we're clearly here, right? I'm using, I think, about 6 computers to give this presentation right now, right? I'm carrying one in my pocket just to keep track of how much I step as I walk around on the stage, and I've got a different one in my pocket that I turned off just, in case I want it later. I'm still carrying it around, right? And so we've clearly entered these later stages. But one of the things that Weiser didn't talk about quite as much is just the sheer amount of data and information that would come with this, right? And so when we take that combination of that exponential growth and the changing nature of computing that comes with ubiquitous computing, we get this paradox where we continually impose ever greater expectations on our technology. We want to access ever greater amounts of information in the world. But we want to do it without spending any time or attention on it. Like, why shouldn't I be able to pull up data from the other side of the planet on my phone on the bus, right? That's a completely reasonable thing to ask, right? But of course it's not, right? It's an incredible thing to be able to do. We keep maintaining this paradox, but as we do it, we have to develop new types of interaction, new models of interaction to address these new scales and types of data. And so if we look back over 50 years of what that's been, right, in the beginning, or at least as far back as we'll go, in the beginning there was the command line, right, and we literally remembered things, and we typed them in by name. But then there were too many for that. And so we developed direct manipulation. We put things on the screen, we recognize them. We don't have to remember them anymore. But then there were too many. We couldn't put them on the screen. And so we put them into hierarchies, right, where we browse down these hierarchies looking for the thing that we think we want. And then for about 30 years now, we've been getting by on keyword search, where we guess a keyword and we hope that that brings us the information that we want. But that's not going to work anymore, right? We're getting new kinds of information where there aren't meaningful keywords. We're getting new volumes of information that we don't know how to access. And we're going to need new models of interaction to go with that. And so one of the things that I want to talk about today then is the potential of machine learning to be that new model. And so I've put Moore's law back up here again with that exponential curve, right? And the line I've added to that is my favorite line to put together with that exponential curve. That's you. It's your abilities. They are flat, right? I will turn 40 years old later this year. My line is starting to slope downward slightly, right? We can't keep up with that curve on our own. And so machine learning is one of these techniques that has the potential to use the power of that curve to pull ourselves up onto it so that we can keep pace with that information and that data in the world. Okay? And so that's the real potential here. The challenge that comes with that, of course, is that machine learning remains this incredibly difficult thing to apply in practice. And so it's hard because it's difficult to understand the relationships between data and algorithms in these systems. It's difficult to make it actually work through this iterative and exploratory process where people try to program with data. And it's difficult to then imagine how these systems are going to behave when we deploy them out into the world, right? When we take them out of our lab and try to make them actually work in practice. They often don't work as we expected. And so the consequence of all of this being hard is that the application of machine learning right now is generally limited to highly trained expert people, right? And as evidence of that, I will note the very, very large amounts of money that these leading companies will pay in order to get access to the people with these skills, right? And that shows just how rare and difficult and valuable these skills are. And what we need instead is machine learning to be something that all of us do every day. And we need new tools that support that will go not only to the experts on the one end, but to everyday people over here as they just go through their life on a daily basis, but to a set of things along the way. So we need to be able to support the creative people, the artists and the journalists. We need to be able to support data analysts as they try to make new sense of new scales of data. And then we need to be able to support software developers and engineers as they make things and draw upon these techniques. And so I'm going to go through a set of systems today to kind of talk about this as a general problem. I put this talk together, and one of the things that we often tell our students is, don't just think about what's going to be interesting in your paper this year. Think about what's going to be interesting in your paper 5 years, 10 years, 15 years from now. And so what I decided to do was go back through a set of systems over the years and look at the story that they tell in building up towards everyday interaction with machine learning. So the first one that I want to talk about is a system named Franz. This was done by Jerry Fales and Dan Olson. It was Jerry's master's thesis. I wasn't actually involved in this work, but it's such a great project to talk about as a starting point for some of this. And so the basic idea behind Franz was that they were trying to create everyday touch surfaces that anybody could configure. And so the idea was that they would put a camera in an environment and that you could then configure things that were seen by that camera to be touch surfaces that would interact with the ubiquitous infrastructure. And so I might configure this surface here to control the volume my microphone, or I might configure something else. And the idea was that everyday people could do this and augment the surfaces in their environments. What they found instead, though, was they spent all of their time, so while that was the research they were trying to do, they spent all of their time trying to get the camera to work. And they spent all of their time trying to get the camera to do skin tracking, which if you've ever tried to do is surprisingly hard, right? Because you have to deal with different skin tones, you have to deal with changes in lighting, you have to deal with shadows and the camera moving and so on. And so what they did is they said they wanted to look at how to quickly train a camera to solve common vision tasks in specific contexts, and they developed Franz. And the idea here was literally to take an image and color on it, like a child, right, with Franz, to color on it to indicate what the things were that you wanted the system to recognize. And so you would take an image like this, you would say, this is a hand, that is not a hand, and it will learn a model. It will give you an update on what it learned. You will then go in and correct that. It will update its prediction. You'll correct that, and it will update its prediction. And so if you see that in video form, you'll see they have this image they've captured, they draw around it to say not a hand. They then switch which color crayon they're using to indicate that they're indicating the hand. They train a classifier. It comes back with a reasonable model, but it's missing parts of the hand. And so they go ahead and correct some of the pixels around the edges. They're then going to train another model. It's going to come back, and it's going to have misclassified some pixels. So you see some of the parts of the book there are being labeled as skin. Franz is labeling every individual pixel in the frame separately, right? So it's classifying every single pixel using some color features around that image. And so now, in about a minute, they have created a classifier that they can use for their problem, right? And they go to another image and see that it's working fine there as well. So that took them about a minute, and they can switch and go and do the classification or do the interaction that they want to be doing. So the thing that's so compelling about Franz is that it casts machine learning as something you solve with interaction instead of with a bunch of offline analysis and data programming, right? And so machine learning is traditionally thought of this thing where you gather your data, you engineer your features, you develop your model, you worry about whether or not your data is going to generalize onto unseen data in the future, and you do experiments to try to do that. And they threw that away and said, I'm just going to make a model that works well enough for me right now. This may not be the best hand tracker. It may not work for a different person. It may not work on a different day. It may not work in a different environment. But it works for me right now for the thing that I'm trying to do in my interactive context. And so I'll give you a second example I developed. Here they were working on augmenting a person driving a robot. So the scene on the right-hand side there is what the robot is seeing as it drives in an environment. And you could steer it. On the left-hand side, they've indicated which surfaces in that scene are safe to drive on and which surfaces are not safe to drive on. And so the robot will stop or steer around something if you accidentally try to drive into something that's not safe, right? So this is a really hard computer vision problem, right? We could spend entire dissertations on trying to model scenes and reason about this. But they didn't do that. They said, well, I'm in this warehouse today. Today's where I'm driving. Today I don't want to drive on the boxes. And so I just draw a stroke across the boxes and say, don't drive there, right? So now it thinks it can't drive everywhere, or we need to fix that. So it say, yes, it is okay to drive on the floor. And it comes back, and now it has a model, right? And it literally took those two strokes to give it a model of where it's okay to drive. And then they pick the robot up, they go outside, they put it on a path outside, and they say, drive on the path. And they draw another stroke to say, don't drive in the grass and don't drive on the people. And that's okay, right? This works. It's not a perfect model, right? If you look at this model currently believes it's okay to drive on the side of the building in the background. This robot cannot do that, right? It is not that cool of a robot. But if that became a problem, you would just make another stroke. It's probably never going to be a problem because as you get closer, there will be grass and stuff in between you and the building and you won't go there. But if it did, you would just draw another stroke, right? And so this was all they needed to solve their interaction problem. And so, in addition to this recasting, Franz makes it work because it applies severe constraints onto the problem. right? The only thing you can do in this interaction is color and draw lines and indicate what should be recognized or not, right? Sometimes you show this work to computer vision people and they get all excited and they want to add new features and new capabilities into the system. And that's true, it could be more powerful, but that would miss the point also, right? The point was to make it really quick and easy to solve these kinds of problems. Don Norman made it into yesterday's talk, so here he is too. And we'll see if he makes it into the keynote tomorrow. But this is something we know how to do as HCI people, right? So the machine learning person would have spent a very long time trying to solve that computer vision problem, where is safe and where is not safe to drive, right? But as HCI people, we can come in and say, well, we know that if we apply some constraints on this problem, limit the set of possible actions, we can reduce the barriers to somebody addressing this problem and let them know what is the right course of action, even though they don't actually know anything about machine learning, even though they've never done this before, okay? And so that's going to be my first takeaway as I go through this, is that the effective use of design constraints can remove expertise barriers to applying machine learning and allow these techniques to be applied by people who otherwise wouldn't know how. Okay, but that came with a trade-off, right? So what we've created, or what they've created with Franz, is a domain-specific interactive tool, right? It makes it really easy to solve exactly one problem. And if you have a different problem, you can't use it at all. It doesn't help you at all. And then at the other end, we've still got the experts, right? They've got their general purpose machine learning. They can solve, according to them, anything, right? But that expertise barrier is still way too high. And so we wanted to look at what can we do in between these two. And so the second system that I want to talk about is a tool called Gestalt. This was K.R. Patel's dissertation work. And what Gestalt looked at was this fundamental classification pipeline. And so this pipeline where you go from data to extracting features from that data to then applying a modeling algorithm and then evaluating the performance of that algorithm is fundamental to many, many different classification problems, right? So I've shown it here with digit recognition, which is sort of a benchmark task. This same model then applies if you go and do document classification, right? The same model applied in crayons. The same model still applies in most of the deep learning contexts that you're seeing people work on now. There's still this fundamental progression from data to features to algorithms. And so Franz proposes an IDE to support that classification pipeline. So this is going to be our constraint. We're going to say we can solve classification problems. We're not doing reinforcement learning, we're not doing unsupervised learning, we're not doing these other kinds of things that machine learning people do, but we're going to take advantage of this pipeline and then build an IDE to support that and support programmers as they solve these kinds of programs. And so it is code, right? We've now jumped over into code. So what makes classification different from any other software development problem? Right? And so we looked at this. I'm going to zoom in on these charts in a minute here. But the fundamental thing here is that when you write a machine learning system, the data is part of the program. Right? So when you write many algorithms, when you write many kinds of code, you can reason about the code, you can reason about its correctness, you debug it with breakpoints, right? You watch individual things happen and you decide if the right things are happening in your algorithm. You can't debug machine learning in this way because the volume of data as a whole is part of the program. It controls the behavior of how the model learns. And so all of your code can be correct, and yet your system might still not work, right? Because the data doesn't answer the right questions. And so this is a 4-hour experiment. This is a participant who gets it right. They have an effective process, they get the right answer. You can see over the course of these 4 hours as they're working on the system, they switch back and forth between collecting data, working on their features, trying different modeling algorithms, conducting experiments to see how they're doing. And on a holdout set we had behind the scenes that they couldn't see, we see them steadily improving in performance over the course of those 4 hours. This is another participant who struggles. So they spend most of their time on feature selection in the beginning. They never pay attention to their data. At the halfway point in this experiment, we gave every participant some additional data. And so at that point, this person realizes, oh, data matters, right? And so they collect a bunch of additional data in like the first 10 minutes, and then you see this jump in their accuracy afterwards as they start working with that data. Okay, and so they had neglected the data part of their answer. They recognize this, they come back to it, and they fix that over the course of that time. And then this is a participant who never gets there, right? And so they stay on feature creation the whole time. They only briefly glance at data, but they never get a good answer. They never get good performance because they are completely missing that part of the problem. And so what we need in an IDE then is to support this iterative process that you have to be exploring. So there's this expression, you know, you're only as strong as the weakest link, right? You've got to be constantly looking at these different parts of your system to identify which part is holding you back. And if you get stuck on one of them, you're probably not stuck on the right one, right? And so you have to go back and forth. And that's what Gestalt supported. So Gestalt combines code with data in the same environment. And so we built this structured pipeline that supported that progression that I've shown you from data to features to models to experimentation, explicitly represented that structure, but then provided the full flexibility of code, right? You could write anything that Python can write when you were in each of these stages. That was connected through a shared data table that we then linked up with visualizations and tagging and filtering, the kinds of things you get in a tool like Tableau or in other visualization tools where you want to be able to inspect your data. But then we could track your data as it moved through your code and give you visualizations at each different stage of your data and how it was being modified as a whole. So you could debug your programs with all of your data and not just with breakpoints. And so let me give you one example of what that enables. This is a confusion matrix. It's a common visualization in machine learning. It tells you how your system is currently confused, what kinds of mistakes it is making when it encounters your data. There is a 123 down here. This means there are 123 cases in the data set where it is saying that something is a square when it's actually a triangle. Okay, and this is a gesture recognition problem. And so a very reasonable question that you might want to ask as the person who's implementing this is, okay, can you show me? Which are the examples that are being confused here? I want to look at those and try to build my intuition about why and how to fix it, right? But with a traditional tool, you couldn't do that because the traditional process and the process that we see in most of the tools now still is that you had your data, you wrote some scripts that extracted some features from each of those, right? That went into a new file. You loaded that file in something else that applied a modeling algorithm and outputted a third file that had the results of your experiment in it, right? And so the raw underlying data is lost. It's been gone for a while. All you have left are a bunch of numeric values that try to summarize different aspects of your data. And so actually seeing your data, getting your human intuition onto that problem is incredibly hard to get back through these multiple breaks. But Gestalt could just support that. And so here you'll see the developer will click into that confusion matrix, that cell in the matrix. The act of doing that applies a set of filters onto the data. They can then go and view the data directly, and they can see these are the examples that are being misclassified. They then can tag them by which study participant provided each of those examples. And with a little bit of inspection here, you can see what's going on is that those two colors correspond to two people who provided gestures, and they just gave the data's mislabeled, right? It's a data quality problem. The data isn't labeled correctly, and so that's what's confusing the algorithm. And so to make this work, what Gestalt did was it allowed a developer to write code to extend the environment. And so the idea is to support developers working on any kind of a problem. Right? They might be working on gesture recognition, they might be working on document classification, they might be working on something with audio, right? But we don't know what they're trying to solve. We just know that we have to support this general pipeline. And so we rely on the developer to be able to write their own code to enhance the IDE to support visualizations of their data. And so in this case, they would take that data table, write some code to produce a visualization of one example in their data. Gestalt then provides the overall visualization that will combine a lot of these to support the underlying process that the person is working through, right? And show you, here's your examples, here's how they're being misclassified and supporting the tagging and filtering. And so we provide that, and we rely on the developer to provide the knowledge of their own individual problem that they're working on. And so what that's doing is taking this idea of constraints and allowing a developer to relax those constraints through the expressivity of code, right? So we have an initial set of constraints, we have an initial set of things that we can support, and both Franz and Gestalt rely on that, because if you don't constrain anything, if it's completely unconstrained, then you can't make any assumptions. You don't know what you can really focus on trying to make more effective. But Gestalt shows that you can take the basic capabilities of the pipeline and then extend it onto new problems by giving the developer that ability. And so that's going to be the second takeaway here, is that this ability to extend a tool can then allow it to address new needs beyond the original intent of a developer. But yet again, this came with a trade-off, right? And so we had crayons, and with that we said, well, anybody can train this kind of a recognizer, right? And now with Gestalt, we're saying, well, anybody who can use an IDE and write code to extend that environment and so on can build a recognizer, right? And that's a much smaller set of people. And so what we need, in addition to these ideas of constraints and extension, is an ability to allow people to interact with data, to express their goals and needs and wants in data in a way that doesn't come with the high barriers that come with code. And what I want to switch over and talk about then in that regard is extending interaction by defining a language. Okay? And I'm going to use the word language very explicitly as I go through this. Right? And so how can we think about giving people new languages for interacting with their underlying data? And so if you go back, I started with this progression earlier, right? From the command line through search. And what we did there is we went from remembering a name to recognizing an object, to browsing for an object, to searching for an object. But you can take those last two and you can unpack them. And browsing is the act of recognizing a name and thinking that it probably applies to the category of object that you're looking for, right? So you see a word and you think, oh, that word is probably the right one for the thing that I'm looking for. And you browse onto that, right? Searching, on the other hand, is actually guessing the name, right? You have to guess a name and think, well, what am I looking for? And can I guess a word that will correspond to that, such that if I issue this search, I'm probably going to get back the thing that I want. And with new forms of data, what we encounter is this problem where, what if we cannot recognize or guess a name? What if the thing that we're looking for, we don't actually have a name for it? Or if we do, that name doesn't work. Or if it might exist, we can't recognize it. Right? So imagine being in a country where the language is different, and even if somebody has a name badge on, you can't read it. I can tell you about it sometime. But imagine that is the way that all of our interaction is going to become with all this new data, right? We can point at it, but we don't have any way to talk about it and to say what we actually want. And so let me give you an example of this. The first example I want to use is a system that we did. This was Salima Amershi's dissertation called QClick. And the context for QClick is that we're searching for what I'm going to call a product image. Right? And so the three images here are all examples of stereos. They come back from a keyword search for the word stereo. Right? They are also examples of product photos. And so I'm going to call a product photo this nice, crisp image of an object on a relatively uncluttered background. Right? And you might want to use that in a presentation or something else. And so how do you search for this? Well, the first thing you do is you go up and you issue the keyword search for stereo. You get a bunch of images back from the engine. It turns out there's this band called Soda Stereo. I didn't know that until I did this research. You get all of their album covers. You get stereo microscope images and stereo telescope images. You get images that are of stereos, but are not product photos. Right? And so overall in this data, only about 10% of the images are the kinds of images that we're looking for. And so stereo on a white background, right? Unfortunately, this doesn't work either. And so only about 12% of these images are this product photo concept, right? And the reason is because of how all of these search engines work, right? So they use keywords that show up nearby in the web page. And so the name of the file, or a caption on the image, or text that's in a web page near where this image is displayed. And nobody puts a file on the internet and names it stereo on a white background.jpg, right? We just don't name things that. And so the problem is, how can I find these kinds of photos? How can I issue a search for these kinds of photos? But the problem is actually more general than that. This is actually a really easy classification problem, right? You can lock a student in a room for a few hours and get a classifier out that will solve this problem, right? You've got a histogram of the pixels in these images there that makes this really easy to identify. The problem is that there are thousands of these kinds of distinctions, an unknowable amount of these kinds of distinctions that people might want to make in their data. And as a developer who's implementing a search system, you can't know all of those beforehand. You can't provide all of them beforehand. And even if you could, then if you were the designer who's trying to think about how people are going to interact with this, you can't have 1,000 checkboxes, right? You can't go to a search page, type in stereo, and then browse 1,000 checkboxes to see which kinds of images you want. That doesn't work either, right? And so what we need is a way for people to express these kinds of ideas and concepts in the data that they're going through. And the way that we did that in Qflick was by interactively training a classifier. And so you would get this initial set of images back, a person could inspect those, and they could say, well, this is an example of a product photo. This is what I'm looking for, right? The system will then update its classifier and re-rank the images in response to that. The person might be done at that point, right? But if they continue to go and they decide they want to work on this some more, they can say, well, this is not a product photo, right? This is an album cover. And so this is not an example that I want. The model updates, the images update, and you have another set of images. And then they might do a third positive example, right? Say this is also a product photo, update the example, and so on. So this is mostly relevance feedback so far, right? Where we're just telling it which results are relevant to our query. But the thing that Qflick did is that it made this product photo concept, it made it a top-level thing, and you could carry it forward. And now if you went and you did a search for telephone or television, you could then say, now show me the product photos, right? And it made this an adjective that applied onto your data. And you could use this adjective to filter and re-rank. And it was now something that said, of all of the images in the world, here's the ones that I want. And I didn't have a good keyword for that before, but now I do because I've trained examples of what I mean by that keyword. And so Qflick was interactively teaching the definition of a concept and then allowing people to reuse that going forward. It was interactively defining a language onto that underlying data. And we did I won't get into exactly how the algorithms worked here. We posed this as a metric learning problem for the people in the room who are interested in that part of it. The idea being you tried to find properties of the examples that made them similar to each other while making them different from other images that were in your corpus, okay? And we did a set of papers where we looked at what are effective strategies for this example-based back and forth. Because all we can do is give the system examples, and all the system can do in return is give us examples. And we have to eventually agree that we mean the same thing, right? And so we looked at how to design for that. But that language was still implicit. And so the fourth example that I want to go to was a system called GestureScript. And the idea here was to make the language explicit and actually talk in language about the underlying data. And we're gonna change context now. We're gonna go to gesture recognition, right? And so the problem here is that a gesture comes in. It looks like that, right? And we have to, and these gestures are the kinds of gestures that you might make with a pen or a finger, and you have to make it without lifting it. So these are called unistroke gestures. And so that gesture comes in, and you have to decide, what is this? Is it a left bracket, a right bracket, an arrow, or a star, or a pigtail? The standard solution to this problem is example-based training. So this arrow comes in, you break it into parts, you compute features at each of those points, usually based on pairs of features and pairs of points and how they relate to each other. You have a library of examples, you have pre-computed these same features for each of those examples. You then compare these feature vectors to each other according to some similarity metric to figure out which one is most similar. And in this case, you decide that this is an arrow 1 because its feature vector is most similar to that other feature vector. And so what GestureScript is going to do is extend this. It's going to preserve that core ease of just giving examples and getting a recognizer, but it's going to extend it with a language that allows you to talk about the underlying structure and form of these gestures. Okay, and you can see a couple scripts here on the side where we say that an arrow starts with a line and ends with a head, and a spring starts with a head, has some number of caps, and ends with a tail. Okay? And the important thing about GestureScript is that it has no idea what a line is. It doesn't have any pre-existing notion of the shortest path between 2 points. You could have called this cat, bird, and dog, right? Those would be lousy variable names. But the idea is you're going to define this language together as you go through it. And so what this allows you to do is it gives you a new form of control. So if you are trying to train your application to recognize these 2 different kinds of arrows because they mean different things, and in an example-based system, if this isn't working, all you can do is give it more examples and hope that somehow it starts working. Right? You don't have anything else you can do. But with GestureScript, you say, well, the thing they both start with a line, and then there is head 1 and head 2, and those are different from each other. And so GestureScript comes back and it learns, well, if these 2 have something in common, and it's called a line, then I think this is what a line is. And they have these different heads that go with them. Now, the other thing that the language enables is interactivity. Right? So you can actually directly interact with its underlying representation. So if it learns this weird notion of a line from the examples that you gave it, you can take it and you can correct it and you can say, this is the boundary between a line and a head. Right here. And prior to having the language, you didn't have any way to communicate that in to the classifier. And so it can learn the right parts. The other thing you can do is demonstrate one of the parts separate from the rest of the gesture. You can say, you're having trouble recognizing a head 2, let me just demonstrate what that looks like separate from the rest of the model. And so it learns that, and then it's able to learn that, well, then this must be a line. And then the last thing is that it enables greater complexity. And so something like this spring, you and I would look at it, and whether it has 3 of these caps, 4 of these caps, 5 of these caps, 6 of these caps, we would still think it was the same gesture. But those all look very different from each other in this similarity space that I've said is how these algorithms work. And so again, you just end up providing a lot of examples and hoping it works. But here we can tell it about that structure, tell it about the caps, and it can fit to the different numbers. And so we'll put that together in a video here. This is how training up a set of recognizers. This first gesture he's going to do is a W line circle. And so this is something you might use for like searching on Wikipedia, right? You write the W and then you go over to where you want to search and you circle the thing that you want to search for. And so he gives it the initial script describing it. It learns a very bad notion of these parts. That is not what a W, a line, and a circle look like, right? So he's going to correct that. He's going to demonstrate a circle once, and then it's going to update its model based on that. So he just does that example up there. That's enough for it to learn a correct notion of a W and a line as well. So he moves on to the other gestures that are in the set that he's training. This is a circle, line, circle gesture. This could be like a cut and paste, right? Circle one thing and then paste it over here. Right? And so the language here is globally scoped. He's already given it an example of a circle and a line in prior gestures, so it's able to use that to learn what he means much more quickly here. He doesn't have to provide as many examples. And so he just inspects that seems to be working. He then goes and he's going to work on his other gestures. So these are the arrows. He's going to define this one as consisting of 4 lines. It's got enough examples of lines that it's able to just recognize these along the way. And he's going to define this other arrow as consisting of 3 lines and an arc. This is the first time he's ever mentioned the idea of an arc as a concept that needs to be recognized. But because it's surrounded by these lines, he's able to get that. So again, I won't go into the details of exactly how GestureScript is implemented, but at its core, what it's doing is trying to solve two problems simultaneously, right? It has these examples and these scripts that describe the structure inside of each example, that this circle, line, circle consists of those three things in order. And it needs to learn where to segment examples into those parts. And on the other hand, it doesn't know what a circle is. It doesn't know what a line is, and so it has to learn that as well. And so it's an expectation maximization algorithm where it solves these two problems simultaneously, but really what it's doing is learning that language. What do you mean when you say circle? What do you mean when you say line? And so to pop out of the details of that, one of the things that I like is that we have an existing theory for thinking about what we were just doing inside of GestureScript. And so if you haven't seen this paper, I highly recommend it. It's some work by Victoria Bellotti on 5 questions for interaction as communication. And these questions are things that have been solved in the GUI. They were solved 40 years ago, and we take them for granted now. But every time we think about a new form of interaction, we have to revisit these questions. So the address question is, how do I tell the computer that I want to talk to it, that I want to interact with it? Right? Attention is, how do I know that the computer is attending to me, that it's listening now? Right? But the two that I'm going to focus on are action and alignment. And so action is, how do I affect a meaningful action, control its extent, and possibly specify a target or targets for my action? How do I say what it is that I want to manipulate? Right? And then alignment is, how do I know the system is doing the right thing? And so we have familiar answers to these questions, right? So in the GUI, we solve action with affordances, right? We put things on the screen that you can point at. This is a place you can take an action. We solve alignment with the mouse cursor, right? The mouse cursor is on top of the thing that you're going to manipulate, where we agree that we're talking about the same thing. In camera-based systems, like the Wii and the Kinect, right? They all employ this trick. They avoid the hard calibration problem. They always show you where you're pointing. They always show you where you're at. And so you can solve this action and alignment problem because the person corrects for it themselves, because they see a mirror image of them being projected back to them. And so we agree on what the person in the system think is happening in the interaction. But these new scales of data, thinking about this language idea, requires us to be able to say, we need to interact with data when we can't put it all on the screen. We don't have enough pixels to put it all on the screen. We can't take that answer. What we need is instead a different way to think about action and alignment in large data, in large personal data. And this idea of a language and being able to define a word that means the things that we're talking about, and we agree about this and they can use it going forward, I think is a key part of that. And so then the last system, or the last space I want to talk about, is in personal informatics, and part of why I think these questions are so important. And so, if you're not familiar, personal informatics is also known as self-tracking. It also is known as like living by numbers, personal data, the quantified self. The personal informatics covers everything from physical activity tracking to smart medical devices that are monitoring you over time, to personal finances, right? All of this stuff where we have data about ourselves and we're trying to get value from that data. And the challenge of personal informatics is that if we take this range of skills and range of expertise, personal informatics takes everyday people and it puts them up in this part of the spectrum that we used to do for data analysts. People who had training and specialized tools. But now, all of a sudden, you and me and everybody else are asked to be there as part of understanding our own health, as part of understanding our own finances. Right? And so, what we do is, right now, we don't design for that very well. We don't know what to do with this data. We don't know how to give it to people. And so you can take something like Fitbit data, where behind the scenes you have this very detailed map of how I spent my day, how active I was throughout the day. But we don't know what to do with that, and so we reduce it down to just badges and number of steps per day, right? And contrast it with something like this. This is a person's step activity every day for a month. There's a pattern in this data. It's really obvious once I tell you what it is, right? But how can a person find that pattern, right? Like, you're more trained than the average people, and it's still hard to find, right? Like, this person usually goes for a run on Tuesdays and Wednesdays. They haven't been doing that lately. That's why their activity is down. Right? These are the kinds of insights that we want about ourselves. And that's just one-dimensional data, right? So this is moves. This is, if you're not familiar, it's an application that tracks everywhere that you go. And it tracks how you get between these locations. And so do you walk, do you run, do you ride a bike, do you take a vehicle, right? Extremely detailed location and transport data. And at the end, they give you this history of how much you walked today. It's the same as the steps, right? It takes all of that data and it just reduces it down to this because we don't know what else to do with it. And this is one of my favorites. This is Saga. This is by a company that has since gone out of business, and so I don't feel bad picking on them as much as I might otherwise. But they bring in all of this data. They had an amazing data collection system. Your location, all of your social media activity, they could pull this all in and give you this highly detailed life log, and they promise you insights from that data. And what they give you are badges. Things like, you live in an apartment or a condo. You work at a university. You are sometimes at the university in the evening, and you take a bus. I know all of these things, right? I don't need to track data for 2 months to learn these things about myself, right? That is not insight to me. And so we did a system called Visual Cuts, where we looked at moves data, and we looked at what are the goals that people have for this kind of data. So we surveyed 113 people about what did they want to see about their activity in relationship to other aspects of their life. You see things about their work schedule, the weather, travel, their sleep, the schedule of their spouse and children, their socialization, their food. These are the questions that people actually have about their activity data. We developed a set of visual cuts. These took your physical activity data and they contrasted it with some other dimension of your data and then put that together in a simple visualization that was intended to support these kinds of questions. And we ran a deployment in which we recruited 14 people. We asked them about their personal questions, their personal goals for this kind of data. They tracked for 2 weeks. They came back. We interviewed them about using moves at that point. We then brought them back 2 weeks later, showed them the visualizations of their data, and interviewed them about that. And we see this shift, right? So they describe just the scrolling history that moves will give you as useless, right? This is like, I was ready to tell you moves is totally useless, but once I see these graphs at the end, I'm like, oh, I can see where you're going. I can see how you might actually want to use this in your everyday life. So we're converting this data into questions that they want to answer. We see self-discovery, right? So, oh, that's cool. 38% of my unique places are food places. That's been a goal of mine, trying to go to different restaurants, trying to try something new. We see opportunities for action. Yes, my husband and I should be walking more on short trips. We should be biking more on medium trips. This is something we can do to improve our activity. So we made a total of 14 of these different cuts. There were 5 of them that just about everybody thought was helpful. Right? So we asked them, we showed their data in these cuts, we asked them to rate that. There was one that nobody thought was helpful, right? It turns out people don't care about trips that start and end at the same location. Like, this is like walking your dog or going for a run. We thought that would be interesting to people, and it's not, okay? So save the trouble there. But most of them are useful to some people and not to others, right? And so what we saw in that was this need to think about the variety of different goals that people bring to this kind of data. How can you take this data and get it into the different questions that different people have, rather than just assuming that everybody has the same question? But we cheated, right? So I told you this was 14 weeks and, 14 participants over 4 weeks. Behind the scenes, my graduate student was frantically coding these visualizations to make them work for these people when they came back at the end, right? And I don't have enough graduate students to do that for everybody, right? We're gonna have to have better approaches. And so I think it's still an open question of how can people explore their data and surface these kinds of insights in this new form of data. And so that's my last takeaway then, is that all of these things about how to make machine learning work, how to make it accessible to people, have to be done in the context of the actual goals that people bring to this kind of data. We need to know what those actually are so that we can support them in the right ways. Okay, so the good news, hopefully, is that when you see those 4 takeaways, it sounds like, well, we need HCI, right? These are the kinds of things that we know how to do as a field, right? We know how to think about the tools, the approaches, the theory for these kinds of questions, right? And machine learning is this opportunity, it is this challenge, but we're actually really well equipped to address it. Okay, it's just another algorithm, it's not magic. But what I want to emphasize is that it's important that we do. And so I put these two examples up earlier, right? I had moves up, and we agreed that moves isn't really useful to people. It doesn't really answer their questions. And yet, moves was bought by Facebook very, very quickly. Facebook is interested in having a continuous location of everywhere that you go, right? I put Saga up earlier. These badges were not interesting to me. They are exactly what a marketing person wants to know in order to know how to segment me for advertising, right? And so there's so much potential here, but right now it's limited to these companies who can afford those experts with that expertise, right? And I don't want to pick on them. A lot of them mean really well. They are trying to do good, right? Not all of them, but most of them are trying to do good, right? And so, but we'll miss a huge portion of the space if we can't get these techniques to everybody, right? If we can't get everybody able to do this, then we're just missing a huge part of the potential of this data, of these techniques. And so, the last quote that I want to use, my last slide here, is actually a quote from Jacob Hoffman-Andrews. And what he says is, there is no Internet of Things. There is only other people's computers in your house, right? And I think the same thing is true of our data, right? I don't actually have personal data. Facebook has my data. MyFitnessPal has my data. Google has my data, and so on, right? And we're creating this world right now of, like the people in this room, and in rooms like this one, are designing a world right now of ubiquitous computing, of really unprecedented volumes of personal data about each and every one of us. And this new kind of personalized intelligence that will be based on that data for each of us. And what we have to decide and what we have to design for and be careful about is that as we do this, we ensure that we don't make that the world is just data about us, right? But that it is actually data for us, and that we can use it and pursue that potential. So that's my challenge for going forward here. And with that, I'd like to, again, thank you for having me, and I think we'll have some time for questions. Thank you.
네, 저희가 시간 관계상 질의응답 화면을 좀 띄울 건데요. 한 3분 정도 질문 주신 내용을 답변을 드리도록 하겠습니다.
네, 질문을 많이 올려주셔서 지금 스크린을 전달해서 한 3개 정도만 선택을 할게요.
So there's a question here of that machine learning-based interaction changes the concept of interaction. What do you think the role of HCI will be when the interface developed is based on these learning algorithms? And so I think I tried to get to that earlier when I talked about this scaling problem, right? And I think in the same way that we now take for granted that we have a device with access to all of human knowledge in our pocket, right? We will eventually take for granted that these intelligences are doing more on our behalf and with less explicit instruction from us. And I think it has to be bidirectional as we design for this. And so I think one of the challenges, one of the hot terms right now is understandable AI or understandable machine learning, right? Can we understand what the system is doing? And I think that's not enough. We have to be able to control what the system is doing also. Right? And so it has to be bidirectional, and I think that's the potential of this language-based approach, is to give us the ability to work both ways inside of that. One more? Okay. So I'm told 1 or 2 more questions, and so there's this question with Franz here. It says, I can remove the barrier to using machine learning, but it's not easy to avoid the overfitting problem. I'd like to know your opinion about that. And I think that's exactly true. It's very likely that many of these models are overfit, right? And so they will work today, and if you move down the hall or you turn the lights off, it won't work anymore. And part of the point here is that can be okay, right? In the right interactive context, you can quickly retrain this and have it work again in the future, right? In your new context. And we saw that with the robots. One thing that I didn't show in the Qflix system, some of the work that we did looked at people training these examples, training the systems through examples over time. And people, everyday people who don't actually know about overfitting, right, would still sense that something was happening as they gave more and more examples. They would give it the first few examples of something like a product photo, and the system would get better and better. And then later, they'd be giving it more examples, and they weren't sure if it was actually helping or not, right? And so one of the things that we saw there was the traditional question in machine learning is like active learning. Is this a positive or a negative example? And you get that judgment from a person and you decide, right? But people don't care about that. A person's task is never train a classifier. A person's task is always something about the images or the application that they're building. And so one of the things that we looked at was how can you allow people to look at different potential models that result on whether you label this as positive or negative. That turns out to just be called undo. It's one of these basic things that we do in HCI all the time, but it goes against a lot of the machine learning ideas that data is valuable. Once we get data, we can never throw it away. We must always hold on to the data, right? And so the general answer to that question is yes, if it overfits, throw it away and start over, right? And that's okay when we're HCI people and when we think about it that way. We get to define the problems that way, not be stuck by how the machine learning people define the problems. Okay. I think we'll think. Thank you again.
네, 이상으로 키노트 마치도록 하겠습니다. 그 좋은 오후 시간 보내시고요. 이따가 저녁 때 HCI 파티에서 다시 뵙도록 하겠습니다. 감사합니다.
네, 그 점심 안내 잠깐 드릴게요. 저희가 30분 동안 포스터 세션이 진행이 되고요. 12시 40분부터 이 자리에서 점심 식사 갈비탕이 제공이 되고요. 저희가 총 문을 3개를 열어둘 거니까요. 줄을 서실 때 3줄로 저희가 문 앞에서 입장권을 뜯은 상태로 준비를 해주시면 빨리 입장이 할 수 있도록 저희가 안내를 하겠습니다. 그러면 12시 40분부터